applications to secure implementations.
Thank you. So if you look at the various techniques for protocol verifications, some techniques rely on the symbolic model, so the Dole-Viao model. Other techniques rely on the computational model, which uses bit strings to represent messages. And some techniques deal with specifications of protocols, and others with implementations. So the more traditional ones and the first ones were techniques that worked in the symbolic abstract Dole-Viao model, and for verifying specifications like FDR, for example, which was the first model checker used to verify the Needham-Schroeder protocol, and more recent ones like Avispa or Proverif. In the computational model, you have tools like cryptoverif or Certicrypt, which relies on the Coq prover. And for verifying implementations, so many of these tools have already been presented by Andy on Monday. So there's FS2PV, which translates. So the idea is to translate the implementation into the Proverif input so that you can then use Proverif to verify your protocol. F7, which uses types. SP2 Java goes in the other direction, so you start from a specification and then you get an implementation by translating it to Java. There are other techniques using VCC, for example, that Andy presented on Monday. And in the computational model, you can start from an implementation in F# and then you convert it to the cryptoverif input, and you can verify using cryptoverif, or computational F7, which verifies protocols using a dependent type system in the computational model. And also by computational soundness, you can transfer some results in the symbolic model into results in the computational model. And what we would like to do in the work I'm going to present is work in the computational model, because it's more realistic than the symbolic model, and also verify implementations of protocols, because even if you prove your specification secure, this does not imply that the implementation is also secure. You can make mistakes implementing protocols, and also the programs have much more detail than the specification. Okay, so our approach is to start from the specification of the protocol and then generate an implementation from the specification. So the idea is that from the same file, you're going both to verify it using cryptoverif in the computational model and to translate it into an implementation using a compiler that we design. So this implementation will be written in OCaml, so I'm going to come back to that. And so the goal is to obtain a proved implementation of the cryptographic protocols. So what we do is essentially the reverse translation as FS2CV. So FS2CV starts from F#, which is a variant of OCaml, and translated to the cryptoverif specification. So in the picture, so we start from the cryptoverif specification. We verify it using cryptoverif. So we get a proof in the computational model. And using our compiler, we obtain some implementation of the protocol in OCaml. We put that implementation together with the cryptographic primitives that we have to write manually. And so the cryptoverif specification gives you precise assumptions on these cryptographic primitives, and you have to verify manually that they satisfy these assumptions. And you have the network code, which you can consider as part of the adversary from the point of view of the proof of the protocol. So you put all this together and you compile it to get an implementation that you can execute. So the choice of the language. So OCaml is perhaps not the most widely used language, especially for crypto protocol implementations. So some motivation, so it's memory safe. So it helps you if you want to have a secure code, because you don't have to worry about perhaps the network code being badly programmed and interfering with the protocol. The memory is separated just by the type system of OCaml. it also has a clean semantics, so that's going to help us proving that our compiler is correct. And actually, there is a crypto library available already in OCaml. So it would be possible also to translate to other languages. So if we want to generate a C implementation, obviously it's possible. Perhaps it may be more difficult to prove that that C implementation is correct if you want to take into account all the problems of memory safety and so on. So some information on.
Couldn't you put a layer of memory safety on top of C somehow and program in C, but yet be in a memory safe system?
So it's not a problem for the code that we generate. Okay, for the code that we generate, if we prove the compiler, then we can prove memory safety at the same time. So it's somewhat, but okay. It's more a problem for the part of the code that you're going to write manually. So for the primitives or for the network code that are going to be in the same program, so in the same memory space as the generated code. And that you need to make sure that it's memory safe. So you could use existing analyzers to verify that, perhaps. So to prove the protocol in the computational model, we rely on the cryptographic prover. So it works, as I said, in the computational model. It can prove secrecy properties, so prove that some variable is indistinguishable from a random number. It can prove correspondence properties, so authentication properties. If the server runs the protocol with some thinks he works the protocol with the client, then the client also thinks he runs the protocol with the server. And all this you can, with all this you can prove the security of a key exchange, for example. You can specify many different primitives using a generic method to specify these security assumptions. So you can specify various versions of encryption in CCA2, in CPA, ciphertext integrity, and so on. You can specify max, signatures, Diffie-Hellman, computational Diffie-Hellman assumption, or decisional Diffie-Hellman assumption, etc. It works for a number of sessions that is polynomial in the security parameter in the presence of an active adversary. And it also gives you a bound on the probability of an attack. So you have two ways of interpreting a proof done by cryptoverif. Either asymptotically, you say that if it proves the protocol, then you show that it's secure against all polynomial time adversaries. Or you, so depending on a security parameter, or you can interpret it as in exact security. So it gives you a formula expressing the probability of breaking the protocol as a function of the probability of breaking each of the primitives and of the number of sessions of your protocol. And so you can run it automatically, or it's possible also to guide the proof by giving the main steps. So saying, for example, you need to apply the security of encryption on the sum key, or the security of signatures on the sum key. And so guiding the proof like that, sometimes you can help doing the proof if the automatic proof strategy does not work. Yes.
If you work with exact security, then this capital N doesn't need to be polynomial. It can be, it's just a function of this capital N. It can be also exponential in the security parameter.
Yes. So if you work in exact security, then there is no security parameter in some sense. So you have the number of sessions, which is some parametric integer. You have the size of the keys, which is also some integer, and so on. And so this tool produces proofs by sequences of games, like those made by cryptographers following Shoup and Bellarier and Ogaway. So in these proofs, the first game is the real protocol that you want to prove interacting with an adversary, and then you transform this game step by step, either by syntactic transformations or using the definition of security of some primitive, and you always arrange so that the difference of probability of breaking the protocol between consecutive games is negligible, or you evaluate it if you want to work in the exact security framework. So you have this kind of situation. You start from the protocol that you want to prove, and you transform it step by step, and the difference of probability is some formula, and in the asymptotic case, you know that it's negligible. And finally, in the last game, the property is obvious just by looking at the form of the game without using any computational assumption. And so you can then prove that the probability of breaking the protocol is just the sum of these probabilities, and you can compute it, or you can know that it's negligible. So to do these proofs, cryptoverif represents protocols in a process calculus. So in this calculus, you have variables that are going to contain bit strings and function applications. So these functions represent functions from bit string to bit string, computable in polynomial time if you are in the asymptotic case by deterministic Turing machines. So on the processes show how to manipulate the bit strings in order to run your protocol. So I'm going to explain that, and I have an example just afterwards. So you have two kinds of processes. So these processes define oracles. So the nil process defines no oracle at all. The parallel composition defines the oracles of Q and the oracles of Q prime. Here you can repeat an oracle n times. So this allows you to have n sessions of your protocol, for example. And here you define an oracle O that takes arguments x1, xn. So this x1 is a bit string inside the type or the set of bit strings, simply t1, xk in type tk, and the computation of the oracle is defined by a process of this form, p. So this process here returns the result m1, mk. So these are bit strings, and q is another oracle definition. So if you end an oracle, you can make other oracles available. So for example, after key generation, you can start a client and a server. So you have the key generation returning perhaps the public keys, and then here you can define the oracles for a client on a server of your protocol. This process represents the end of the protocol when it does not return anything and suffer an error, in fact, that is represented like that. Here you generate a random number inside the type t, and you store it in x, and then you run p. Here you compute some bit string m, and you store it in x. You have the test, that test if m is true, and then you run p or p prime. And here you have constructs for tables of keys. So you can insert a tuple in some table here, and then run p. And here you look for an element of the table x1, xk that satisfies some condition. So for example, you look for the key of some participant of the protocol. So let me consider a very, very simple example of protocol. So I just want to send from A to B the encryption of some random nonce, for example, encrypted under a shared key KAB. So to do that, before actually sending that message, I need to generate that shared key KAB. So here I have a process that chooses some random coins inside this k-seed set, and then computes using the key generation algorithm the shared key KAB. So this key is not returned, so the key generation part returns nothing. And after that, you have a process for A and a process for B, and both of them are repeated n times. So you can run this protocol several times if you like. Then the process for A, what it does, well, it generates the nonce R. It generates random coins that are used for encryption. And then it encrypts that nonce under the shared key KAB and using the random seed S. This nonce to bit string is just a type conversion that does not transform the bit string, but it transforms something of type nonce into something of type bit string. You can ignore it if you like, it's not that important. And for B is going to receive the message and decrypt it. So B is going to decrypt M under the shared key KAB. And there are two cases, either the decryption succeeds or fails. So if the decryption fails, it returns a special symbol bottom, and otherwise it returns a real bit string. And this function is the injection from bit strings to bit strings union bottom. So if it does not return bottom, then the result is of the form this injection of some value, which here it will be a nonce. So this means that you decrypt and then you test if the decryption succeeds, and if it succeeds, you store the result in the nonce. So to summarize everything, you have the code here of this protocol in cryptoverif. Obviously, there are a few other declarations, so you need to declare the assumptions and the primitives and so on. But, I omitted that part. So when you want to translate that into an implementation, you need to add some more information, because here you have three things. You have the key generation, you have the role of A, and the role of B. And these are different programs that you want to run separately. So to show that, you annotate your processes with here PA. So it's the beginning of the program for A that continues until here. And similarly for B, you start the program here and it ends here. And the key generation program starts here and ends here. Okay? And there's one more thing we need to do. Here we generate a key, KAB, but we use this key in A and in B. So we need some way to transfer the key from one program to another, and so we can do that using files. So here we declare that the key KAB is going to be stored in the file, so you give a name, so for example file KAB, and automatically cryptoverif is going to read the key from that file when it needs it here and here. So one more thing you need to specify is the implementation of the various cryptographic primitives on the various types. So for example, you can specify that the type kseed is going to contain 128 bits, so bit strings of that length. Or you can specify that say a type host is NA bit string, so it's the camel type string. And you can specify the serialization functions if you like. So these are the identity here. So these functions are used when you store in a file, for example. So if it's a bit string, then it's easy, you just write the bit string. But if you have a pair, for example, of some secret key and some public key, and you want to store all this, then you need to define how you convert it to a bit string and in which format you write it in the file. So this is defined by the serialization and the serialization functions. And for the cryptographic primitives, you also need to specify which function you use. So for example, here this says that the key generation function in cryptoverif is implemented by this simkgen function in OCaml. And similarly for others. So this function has an inverse. So this injection converts from bit string to bit string union bottom, and this one does the inverse. It converts the bit string union bottom to bit string if it's a bit string, otherwise it raises an exception. So when you make a correspondence between the cryptoverif function and the OCaml function, this means that the OCaml function needs to satisfy the assumptions that you gave in cryptoverif about the primitive. So for example, for encryption, you specify in cryptoverif that when you decrypt the encryption with the right key, then the decryption succeeds and you get the clear text. And you specify that your encryption scheme is, for example, in CPA and in CTXT, so it satisfies ciphertext integrity. So you need to manually prove that your functions in OCaml satisfy these assumptions, probably from some computational assumption. So tables of keys. So this get and insert processes on all tables of keys. So insert, for example, insert inside the key table HK inserts an element HK in the key table. So this says intuitively that the key K is the key for the host H, for example. And the get process reads the key table and it stores in the pair h prime k prime an element of the key table such that h prime is equal to h, and that's it. So this get process gets the key for h, because it's going to get a pair that corresponds to that host h. And if it finds such a key, it's going to run p, and if it does not find such a key, it's going to run p prime. So these tables, we also need to store them in files. So this is specified like that. So you store the key table in the file named here. So for those of you who know cryptoverif, cryptoverif in fact uses arrays internally instead of tables to represent the contents of variables. So when you have several copies of the same process, the variables of each copy are stored in a different cell of an array, and you can use that feature to code key tables. So for example, instead of inserting an element in the key table, you define an array that contains that element. And here in this example, the process is replicated, so you have n cells of that array that store each of the elements that you insert in the key table. And then when you do a get, what you're going to do is look inside this array for an element that satisfies this condition. And this lookup is done by a find construct in cryptoverif. So this finds an index u such that the variables key table 1 of u and key table 2 of u have been defined. So you have inserted the element in the table. And the first element of the table satisfies the condition, so it's equal to h here. And in that case, you can define h prime to be k table 1 of u and k prime to be k table 2 of u, and you continue. So this simulates the get and insert, so get and insert did not exist in the cryptoverif language, and we added it because it simplifies the implementation, and we encode it into the original cryptoverif language like that. So obviously this example is for one insertion. You can generalize to several insertions by looking up at the variables you use at each insertion. So it simplifies a lot the translation to implementations, because you can really use variables as bitstring and you don't need to consider arrays all the time. And it's also more intuitive. So usually cryptographers don't use arrays, they use lists to store elements, which are very similar to tables. Okay, so how do we generate the code for such a language? So these oracles, in fact, are very similar to functions. So the OCaml, the compiler is going to generate a module with functions, with a function for each oracle. So we have first a function init, which takes no argument, so its type is unit, and it returns a tuple of functions corresponding to all oracles that are available at the beginning of the program. And if necessary, it's going to read variables from files. So for example, if you have this KAB key that is written in a file, it's going to be read at initialization in the processes for A and B. And then each oracle is going to be represented by a function. So this function takes as argument the arguments of the oracle, and it returns the result of the oracle and also the functions of the oracle that follow. So if I take an example for this process A, it's an oracle that takes no argument and returns a bit string, and there's no oracle that follow. So in that case, OA has type unit because it takes no argument, a unit because there are no functions afterwards, and it returns a bit string. And the function init takes nothing and returns an oracle OA, in fact. So we have to be a bit careful what we can run and when we can run an oracle or not. So when an oracle is under replication, we can run it several times. So it's just an ordinary function. But when the oracle is not under replication, so you can run it only once. And in that case, we have some encoding trick to make sure that you cannot run it several times. So we define a boolean that is true at the beginning and that becomes false when you call the oracle. So when you call the oracle, you verify that this token allows you to call the oracle, and then the token becomes false, and then you execute the oracle. And if it was already false, this means that you have already called the oracle and you cannot call it another time, so then you raise an exception. And then you have the translation, so you translate a variable into a camel variable, you translate a function evaluation in cryptoverif into a camel function call. The random number generation, you store in the variable x the random function. So this random function depends on the type of the random value in cryptoverif. So for example, if you have 64 bits nonces, you're going to generate bit strings of 64 bits. Here you store the value, the result of m in x, and then you continue. You have the test. This end raises some exception. And finally, the return returns the translation of the following processes and the result of the oracle. And the point I did not detail is that when you compute some variable x, and this variable needs to be stored in a file, then obviously you're going to write it in the file at this point. So you have the translation for the table insertion. So in fact, it uses a function that is defined in the library to just insert the value. These values are serialized so that they are always converted to bit strings, even if the internal OCaml format is not bit strings. And when you read from a table, well, you have a function that filters all elements of the table, so you deserialize the elements and you filter them according to the condition m, in fact. If the condition is true, then you keep the element, otherwise you raise an exception. And you have this function that uses that to get the elements from the table. So if the list, so this returns the list of the elements of the table that satisfy the condition. If the list is empty, you have no element, so you execute the else branch. Otherwise, you take a random element that satisfies the condition and you execute the then branch P. So we need to have some assumptions on the code for this to be correct. So one thing is that we must not use unsafe OCaml functions, such as obmagic, which allow you to bypass the type system and to break the memory safety of OCaml. You also must not mutate values that are received or passed to the functions that are generated by cryptoverif. So this can be guaranteed by using immutable types for the arguments, but it's not very convenient in practice, because in practice, in OCaml, most bit strings are represented by the type string. So all the functions that are in the crypto library or the functions that send bit string on the network use that type string. And that type is mutable, so we have to be careful about that. We also must not fork processes in the middle of the protocol, essentially. So it's okay to fork the server at the beginning, which we usually do. But after that, you should not fork just after receiving an oracle that you can call only once, because then that would allow you to call it several times. You also assume that the programs are executed in the order that is specified in the specification. So for example, you must run the key generation before the client on the server. You must not run in parallel programs that insert data in the same table, because that may corrupt the table. So that can be guaranteed using locks, for example. We also assume that the types that represent cryptoverif data structures are not recursive, because we make comparisons on these types in OCaml that could lead to a loop. And we also assume that the files that we use in the generated code are not read or written by other code, possibly an adversary in getting into these files. So obviously, if the adversary can read your secret keys, then the security is lost. So we applied this framework to the SSH protocol. So let me remind you the structure of this protocol. So it consists in fact of 3 protocols. So there's the SSH transport layer, which starts with a Diffie-Hellman key exchange, and it uses the established shared key to build an encrypt and MAC tunnel. And then inside, so this SSH transport layer authenticates the server, but it does not authenticate the client. And so the first thing we do after establishing the tunnel is the authentication of the client. So you can do that by several means, by giving a password or by using a public key, for example. And after that, you can run any application that is going to use the tunnel for secure communications between the 2 machines. So the protocol we have considered is the version 2 of SSH. So in this protocol, let me remind you of the key exchange protocol. So you have a client and the server. The client sends an identification string saying SSH 2.0 and some version, so saying, for example, OpenSSH or some similar indications. The server does the same thing. Then the client and the server send a key exchange initialization message which contains some random cookie, some random nonce, and a list of algorithms. So the algorithms that we use in our implementation are Diffie-Hellman group 14, so it's a particular Diffie-Hellman group using the hash function SHA-1, so this defines the key exchange message. Then the signature is SSH RSA, and you have the encryption scheme, which is AES in CBC mode, and HashMac using SHA-1 as a MAC for the tunnel. So these are the ones that we use in our implementation. It's possible to have several algorithms, and the client and the server negotiate the algorithms. So they're going to take, I think it's the server orders the list of algorithms by preference, and the one that is taken is the first in the list of the server that is also accepted by the client. And then you have the key exchange itself. So in that key exchange, the client chooses a random exponent x, computes g to the x, and sends this kdh init message with this g to the x exponential to the server. The server similarly chooses a y, compute g to the y. From that, the server can obtain the common key, which is e to the y, that is g to the xy. Then it's going to compute a hash of the whole transcript of the protocol, essentially. So the identification messages, the cookies, algorithms, also the public key of the server, the exponential of the client and the exponential of the server, and the common secret g to the xy, which is k. And the server is going to sign this hash using its secret key. And it sends the kdh reply message with the public key of the server, the exponential g to the y, and the signature of the hash under the secret key. So this is received by the client. The client now has the f, which is the exponential of the server. He can compute f to the x, which is equal to g to the xy, and which is also the common secret. The client and the server now share this common k. It looks up in some table the public key of the server. So this is a point in which when you run the real SSH program, you can have a message saying this key is not authenticated. Are you sure you want to connect? And this is because the client does not know this public key PKS, so he wants you to approve that public key. So if you approve a public key that is not correct, you have no security at all. And the client is also going to verify the signature of the hash, which is again computed in the same way. With so it's going to verify if the signature is correct using the public key. If the signature is correct, the client sends a new keys message saying I want to start using the new keys, and the server confirms also with a new key. And then you have the tunnel. So the tunnel is established by computing IVs for encryption, so initialization vectors for the CBC mode encryption, using SHA-1 of the common secret, the hash that was computed in the previous slide, some constant A, and the session ID, which is in fact equal to the hash. So these occur twice. This is because there is a rekeying system, and in the rekeying, the session ID remains the same, but the hash is going to change. I'm not going to go into the details of rekeying. So you have an IV for going from the client to the server, and another IV for going from the server to the client. And similarly, for the encryption keys, you have two encryption keys, one in one direction and the other in the other direction. And again, for the MAC, you have two MAC keys, one from the client to the server and one from the server to the client. And then to send some message, some payload, SSH builds a packet consisting of the packet length, some padding length, because we use a block cipher, so we need to pad so that the length of the packet is a multiple of the length of the block cipher, the payload that you want to send, and some random padding. And then the client sends this packet encrypted under the shared key KENC for the client to the server using the IV, and the MAC using the MAC key, some sequence number, so it starts from 0 and then it increments to be able to order the messages for sure, on the packet. And so the MAC guarantees the authenticity of the message, and the encryption is going to guarantee the secrecy informally. And the server does the same thing using the other keys for the other direction. So we model this protocol in CryptoVerif. We also prove the authentication of the server to the client. So the proof is automatic. You specify the authentication property using some events that express that the server thinks it talks to the client, and that the client thinks it talks to the server, and you prove correspondence that if the client thinks it talks to the server, then the server also thinks it talks to the client. So that authenticates the server. The authentication of the client we cannot prove because that's the job of the authentication protocol that we have not modeled for now. For the secrecy of the shared key, we cannot prove it yet, but it's a small extension of CryptoVerif that we need, so we hope to be able to do that rather soon. For the secrecy of messages sent over the tunnel, in fact there is no hope to prove it because there are known weaknesses in the transport protocol. So two problems. One problem is that when you receive a packet, so let me explain, when you receive a packet, you need first to know the packet length, which is here, to determine until when you need to read your message before you can check the MAC. So to determine this packet length, since this packet length is encrypted, you need to decrypt the first block of the message. And so for that reason, you can leak, in fact, the packet length. What you do is that you send some ciphertext. The SSH is going to compute the packet length by decrypting the first block. And then what you do is you send blocks until you get an error. And when you got an error, you know that you reached the length that was the result of the decryption of the block that you sent. So that leads to an attack that was published, for example, by Kenny Patterson and others. And so that's one problem. And the other problem is that we use CBC mode with chained IVs. So this means that the initialization vector for the next message is the last block of the ciphertext of the previous message. But that breaks the INCPA property of the encryption, because the adversary knows the IV before seeing the next messages. So I think it's important to notice that such problems appear when we try to do the proof. So it's not just that cryptoverif is not strong enough, is that there are problems, and that when you try to do the proof in cryptoverif, you see that these problems appear. So this problem appears because the interface, in fact, of the encryption in SSH does not really match the interface of the INCPA encryption, and this is strongly related to this use of CBC mode with chained IVs. And also the length of the packet is leaked because you have an oracle that explicitly returns the length of the packet, so it clearly appears in the model. So to complete the implementation, we had to implement obviously the cryptographic primitive. So this implementation is based on the cryptographic library of OCaml, which has been written by Xavier Leroy. We also need to write some network code to deal with the details of sending packets on the network for the client, for the server, and we also written some code to encapsulate the key generation. And all this call the code generated from the cryptoverif model. So our implementation respects the bit format of the protocol, so we have checked that by interacting with other implementations, particular OpenSSH. Still, our implementation is not complete because we did not implement the key re-exchange, and also we ignored the ignore and disconnect messages of the protocol. So this could be improved. So let me show you a demo. So I'm going to show you briefly the SSH specification in cryptoverif. So these are a bunch of types for keys and signatures and so on. So I'm not going to detail everything, but so for example, here you have the CDH assumption, which in fact just calls a macro that is defined in a library and that specifies the CDH assumption. So you have the definition of MAC here, symmetric encryption, hash functions, so we assume collision resistance in order to prove authentication. Signatures, which are unforgeable under Trojan message attacks. You have these implementation declarations that declare for each type the corresponding camel type, for each function the corresponding camel function. You have the specification of the authentication property that we prove, and finally the code for the server here. So it returns the keyx init message, and then it expects the keyx init from the client and returns the key.dh init and returns the key.dh reply. And then you have the tuner here. And similarly for the client, so you have it returns the key exchange init message for the server and then expects the key exchange init message from the server and replies with the key.dh init. And that's it. And here you have the key generation part, which generates the signature key for the server. Okay. So let me first. So I recompile everything here, and the first thing we do is we check the protocol. So the time it takes, in fact, is the time of compilation afterwards. But so here it says, I don't know if you can see it, but it says that it proved the correspondence that the event in the client implies the event in the server. And it gives you a bound depending on the probability of breaking the signature and the probability of breaking collision resistance of the hash function. And then it compiles, so here it generates the code for the server, the key generation, and the client, and it compiles everything using the OCaml compiler. Okay? And now let me start. So here I send a program, I run a program that just listens on port 4000 for some messages. Then I'm going to start the server. So this server is going to listen on the local machine on port 2222 for a user, which is myself, and using my RSA public key as authentication for me. So I've implemented we have implemented both the transport protocol and outside of CryptoVerif we have implemented the connection so that we can start using the protocol. So and so I authenticate myself using some public key, RSA public key. Okay, start the server, start the client now. So the client is going to contact the server on the local machine on port 2222, so that's the server I've just launched. Is going to use my username with my RSA secret key, and then it's going to do port forwarding, listening on port 3000 and sending all messages on the local machine on port 4000. So this is the port I'm listening here. So let's start the client. Okay, so the client has sent the messages. So this is some debug information that I print just so that you see something. So here this is the identification string SSH 2.0, and that's the CV implementation. Then you have the key exchange init message with the various algorithms, so Diffie-Hellman, group 14, and the SSH RSA, and so on. So this is the one of the client. Then you have the one of the server. Then you have the first Diffie-Hellman exponential with some additional information, and then the reply from the server, which represents the second Diffie-Hellman exponential with the signature and the new keys and so on. And finally, it authenticates the user and it succeeds. Here you have the same thing for the server, so I'm not going to detail everything. Okay, and now I start something that is going to send messages on port 3000. So this means that it's going to send messages to the port I'm listening here in the client window. So it's going to establish the port forwarding between the window here and the window here. And so I can type, for example, Newton, and it appears. So it is sent in the SSH tunnel, so it is sent first to the client. In fact, the client sends the server to the server in the SSH tunnel that message. So this is the clear text, and this is sent encrypted. Then the server receives it. So you see the same clear text here, and you get the message on the other side. So see that it works, and you can test in the other direction if you like, in the same way. And just to test interoperability, let me rerun the same thing, but now I'm going to use my server, but the standard OpenSSH server. So I say to that server to do the same thing, so it's going to contact, so this client, is going to contact the server on port 2222, so that's my server, and it's going to do the same port forwarding from port 3000 to port 4000. Okay, so you see the debug messages for my implementation. Obviously, the SSH standard server, standard client does not have the debug messages. and I can do the same thing. Whatever I type here goes to the client and then server and then back. Okay. Okay, so to conclude, so our goal is to use a single cryptoverif specification that is both proof secure in the computational model using cryptoverif and also translated to an implementation. So we think that it's a good approach because what you're going to do is first specify your protocol formally, then you prove it, and finally you implement it. So we think that it's a good design methodology to first do the proof and then implement, and not in the reverse direction. So what is in progress is to do the proof of this compiler, because obviously right now we proved the specification, but the compiler is not proof correct. So this is in progress. We have done a good part of it, but we need to finish that. And some extensions of the specification language would also be useful. So for example, to use protocols with loops, with mutable variables in the middle, and so on. So to do that, we need to extend both cryptoverif itself to handle these features and also our compiler. So that's all I wanted to say. Thank you.
Questions?
So I think this is fantastic. Firstly, could you compare with using FS to CD or that methodology that you in a sense write your formal specification as code? Because we know camel code ain't so far removed from cryptographic code, and then you compile it to some form that can be analyzed automatically.
Yeah. So well, essentially you get almost the same limitations in that you handle a subset of the F# language, and the cryptoverif language also has some limitations in the language that you can handle. So perhaps the difference is starting from cryptoverif, it's clear what the limitations are, because you handle the full language of cryptoverif, but it's clear from the start what the limitations are. When you start from F#, perhaps you need to tweak it to get into the right cryptoverif model, and perhaps this is more difficult than in the other direction. So that's basically the motivation that if you start from F#, essentially you need to fix a subset and translate it, and we think that starting from the specification is easier. You know what your specification language is from the start, and you can compile it.
But the usual counter-argument is that, I mean, I take your point that it's maybe confusing for users if they're inside F# or Camel, that some of what they write isn't going to be verifiable. But you can ameliorate that by having, error messages. I mean, research tools often don't do a very good job of that, I admit. But if you put serious engineering into, or relatively serious engineering, you can warn the users that are going out of that mode. And on the other hand, the advantage is that you've got all the tooling, if you want to debug the thing when you're actually running. I mean, okay, but I have a question there. I mean, what was it like actually debugging this so you could interrupt with SSH?
So, well, for debugging, you can, well, first of all, you can insert debug messages in the generated code if you want to. And in practice, in fact, just printing the messages that are sent and received at the interface of the generated code is enough to debug the system, at least in experience. But I guess these two approaches, in fact, are fairly similar.
Also, I suppose.
There's a question in that.
How do you model algorithm negotiation?
So right now it's very simple in our case because we have a single algorithm for each. Our implementation supports a single algorithm for each element. So even if we interact with a server or a client that supports several, we know which one is going to be chosen. if we want to do something more general, we can obviously, but it gets somewhat more complicated. So in fact, that part of the negotiation can be included in the network code that we write manually, and then we just need to verify. We need to have several implementations of the rest of the code to accommodate the different algorithms. That's basically the idea.
So what corruption model do you have for the keys? Do you have static corruptions or dynamic corruptions for session keys?
So right now we don't have dynamic corruptions. We have static corruptions.
And how is it modeled?
So for now it's very simple, in fact, because since we don't have authentication of the client, it's enough to have a single client interacting with a single server. The server has no specific secret because the server accepts to interact with any client.
Okay, so just use loggable database.
Yeah, so right now it's very easy, but it would be more complicated to model it, but it's feasible to model static corruptions.
So following on from Andy's question, I was wondering how easy it would be to integrate this with kind of normal debugging. Because compilers normally generate this extra information to put in the object file for use by the debugger, so you can. I'm wondering how do you think it's made it quite a lot harder to do that by sort of managing an extra stage of going through the.
So, and I'm sure I understand the question. So you want to have debug information in the compiled code, or?
Right. So like for other programming languages, you've got a source level debugger. So the debugger can translate back the state of the registers and what the program counter is back to what was happening at the source code level.
Okay, so you would like to have some debugging that goes back to the cryptographic specification. Yeah.
Yeah.
Well, obviously we don't have that right now. Yeah, I think that's an interesting idea, so probably worth looking at.
Last question.
Okay, this is probably a formal methods question. I agree with Andy that this is brilliant, going from a specification to an implementation, but I could also argue that you're cheating a little bit, because your specification language has an obvious operational interpretation, it has no non-determinism in it, no other specification. So it's what you're doing is writing a compiler for a language that we didn't usually think of as being translated. But okay, the question is, do you see perspectives for extending this work in the direction of less operational specifications? Like specifications that just say we like to establish that before the communication this was the case, and after the communication has happened we are now in a different state where...
Yeah, well, so that's a personal point of view, but I see it as a quality that specifications like the applied pi calculus or the cryptographic language have an operational semantics and are programs in some sense. So what you're aiming at is perhaps more something like protocol generation, in which you want to specify your security goals and then you want to generate the protocol from that. So there are some works on these kind of ideas. So there is an early work by Song using Athena, for example, for that purpose. Yeah, I don't know of many recent works on this approach. But,
I would argue that you're making a step on the way, but the hard step is the next one, maybe. Well, I've not made progress on that one, so I can say that.
Okay. Thank you again.
Thank you.